Let's recapitulate the content of our lectures up to now. We've started with holomorphic functions, in particular functions from the complex numbers into the complex numbers that are differentiable in a certain sense. And then we focused on complex integration, that is, the integration of such functions along curves within the complex plane. Third, we've taken a look at Lorentz series. So we've seen that we can describe holomorphic functions in terms of power series. And all these tools then led to the development of the residual theorem. And finally, our last topic up to now has been the Laplace transformation, which again has built up on the previous topics. The Laplace transformation is a fairly powerful tool in the analysis of ordinary differential equations. So you might say everything we have done up to now has been done to build up towards ordinary differential equations. The first few topics have been the stepstones towards the development of the Laplace transformation, and now we will apply the Laplace transformation to ordinary differential equations. Now, before we proceed, what actually is a differential equation? Now, to put it shortly, a differential equation is an equation in an unknown function and its derivatives. So we have an equation where we have an unknown function, let's say u or y or however we call it, and that equation involves its derivatives, and our goal is to find a function satisfying that equation. You could say that differential equations are probably the most important field of mathematics, and it's central in many applications. So we could say that 90% of all mathematicians work on topics that are somehow related to differential equations. And differential equations show up in all sorts of applications. For example, in physics, in engineering, in biology, in finance, in stochastics. Generally speaking, differential equations are quite difficult to solve. And corresponding to that, there's a multitude of solution techniques and different approaches, a few of which we will touch upon in upcoming lectures. For example, as already mentioned, we will use the Laplace transform to solve ordinary differential equations. Later on, we also have a look at Fourier series and the Fourier transform, and there are many, many more techniques that people have developed over the centuries in order to get a grasp of differential equations. So let's have a look at some very important example. We start the discussion of differential equations with a first-order initial value problem. So consider the initial value problem y prime of t plus a y of t equal f of t, where t is some positive number denoting time. And we have got initial values y of 0 equal y naught. So in order to fully parse that equation here, first we notice a and y naught are just some real numbers. A is some coefficient, could be negative, 0 or positive, and y naught is just the initial value. And last but not least, f is a function defined on the non-negative real numbers mapping into R. So how should we think of this initial value problem? Basically, we have got a function y which depends on the time variable t, and we only know a few things about this function. We know at the initial time t equals 0, it assumes the value y naught, and we also know for all positive times, well, we don't know the function explicitly, but we do know it satisfies this differential equation. The first derivative of y plus a times y itself equals some function f. That differential equation is true for all positive times. Now, the function y is not known explicitly yet, so we would like to know, okay, does such a function actually exist? We only have this implicit description of the function y, but we would like to see whether the function exists at all. And then we also want to know whether the solution to that differential equation is unique. Does there exist a function solving that differential equation? And if yes, we would also like to know how many functions solve the differential equation. For example, is there a unique solution? Before we proceed, let's have a look at a physical example. Suppose that y of t is the amount of radioactive material in a nuclear waste dump. Let's say at time t equals 0, we start with some amount y0. And let's also assume that the waste experiences exponential decay. That is, there's some parameter lambda greater than 0, such that y prime of t equals negative lambda y of t, where t is just a time variable. So at t equals 0, we start with the amount y0, and then the amount experiences this exponential decay. Perhaps you remember the solution to that differential equation, because exponential decay and exponential growth are quite central topic in applied mathematics. But even if you remember that, let's also have a look at a variation of that problem. Namely, suppose f of t describes an additional inflow or outflow of radioactive material at any time t. Additional inflow if f is positive, and outflow if f is negative. So maybe there's additional radioactive waste dumped into this container, or maybe we extract some radioactive material. So this inflow and outflow, of course, may vary over time. And in that case, y of t solves y prime of t equals a negative lambda y of t plus f of t. That's another differential equation. And similar processes of exponential decay and exponential growth with some slight variations can be found, for example, in biology or stochastics or finance. It's quite a fundamental process. As already mentioned, the basic questions in the discussion of differential equations are whether the solution exists, and if yes, whether it's unique. Now, it turns out actually showing uniqueness is often much simpler. So let's do that one first. To show the uniqueness of the solution, suppose that we have got two solutions of the differential equation of the initial value problem y1 and y2, defined for non-negative real numbers into R. So that means that y1 prime of t plus a1 of t equals f of t, with initial values y1 of 0 equal y0, and y2 prime of t plus a times y2 of t equals f of t, again with initial values y2 of 0 equals y0. To show that the solution is unique, we suppose that we've got these two solutions, and then we will show that y1 and y2 are actually the same. For that purpose, let's take a look at the difference, which we call z of t equals y1 of t minus y2 of t. Z of t is the difference between the two solutions, and that difference actually solves an ordinary differential equation on its own. We see that z prime of t plus a z of t equals 0, with initial value z at 0 equals 0. In order to show uniqueness, it suffices to show that z of t equals 0 for all times. That is true because y1 and y2 satisfies the same differential equation with the same initial values. Showing that z equals 0 is a bit technical. We take a look at this differential equation, z prime of t plus az of t equals 0, with initial data z of 0 equals 0. Now we multiply the differential equation by some factor, namely z of t times the exponential of 2at. With that, we make the following observation. 1/2 of the time derivative of z of t squared times the exponential of 2at equals z prime of t times z of t times exponential 2at plus a times z of t squared times exponential of 2at. In taking the derivative, we just apply Leibniz rule. We just apply the derivative over the two factors. And now we see that we can factor out z of t times 2 exponential at. And that gives us z prime of t plus a z of t multiplied with z of t times exponential 2at. And that first factor equals 0 because, after all, z of t satisfies the differential equation. What that tells us is that the time derivative of z of t squared times 2 exponential at times exponential of 2at must be 0. In other words, the function z of t squared times exponential 2at is constant. And now things are easy. That function is constant, and for t equals 0, it just equals 0 because of the initial data of z. And so in particular, z of t squared times exponential 2at is 0 for all times t. And of course, since this exponential function there is always positive, it must be that z of t equals 0. And that, after all, had to be shown. Okay, that is shown that the solution, if it exists, is actually unique. But now the question is, does a solution exist? As already announced before, we will use the Laplace transformation to solve this differential equation. In order to simplify the notation, we define the Laplace transformation of y and f. Capital Y of z equals the Laplace transform of y at z, and capital F of z is our notation for the Laplace transform of f of z. The idea is that we apply the Laplace transformation to the entire differential equation, to both sides of the differential equation. Thus, starting with y prime of t plus a of yt equals f of t produces the Laplace transform of y prime of t plus the Laplace transform of a of y of z equals the Laplace transform of f of z. We can use linearity of the Laplace transformation and our knowledge on the Laplace transform of derivatives. That gives us z Laplace transform of y of z minus y at 0 plus a times the Laplace transform of y of z equals Laplace transform of f of z. Now, using our notation defined above, we can write this compactly as z capital Y of z minus y naught plus a times capital Y of z equal f of z. So we've transformed this differential equation into an equation just involving the Laplace transforms. In particular, there are no derivatives anymore. And now we can isolate y of z. So any solution has got the following Laplace transform, namely y of z equals y naught plus f of z divided by z plus a. Okay, so far we have obtained some knowledge on the Laplace transformation of the solution. Now we will use that knowledge to actually reconstruct the solution from the Laplace transform. In other words, what we want to do is we want to undo the Laplace transform and obtain the original function y from capital Y. For that purpose, we need to take a closer look at the Laplace transformation. We have that y of z equals y naught plus f of z divided by z plus a. And to simplify that, we divide this fraction. This fraction is the sum of y naught plus 1 over z plus a plus 1 over z plus a times f of z. At this point, it's helpful if we know a few inverse Laplace transformations, or if we have a lookup table for Laplace transformations and know some rules of calculation with Laplace transforms. So on the one hand, we remember that the Laplace transformation of exponential negative at equals 1 over z plus a. That's one of the factors that we see above. Okay, that already looks good. In particular, that produces already the inverse Laplace transform of the first factor of the first summand. And on the other hand, we remember this convolution theorem. We have got 1 over z plus a times capital F of z. And that obviously is the same as the Laplace transform of exponential negative at of z multiplied with the Laplace transform of f of z. And the convolution theorem tells us that the product of two Laplace transformations is the Laplace transform of the convolution of the original functions. So we see that this product equals the Laplace transform of exponential negative at convoluted with f at z. If you don't remember what is a convolution, we will see that on the next slide. Without that, we see that y of z equals y naught times Laplace transform of exponential negative at z plus the Laplace transform of exponential negative at of z multiplied with the Laplace transform of f of z. The last term can be rewritten as the Laplace transform of the exponential negative at convoluted with f. And now we can use linearity. So we see that capital Y of z is the Laplace transform of y naught exponential negative at plus exponential negative at convoluted with f at z. So far we've taken a look at the Laplace transform of the possible solution, and we see that Laplace transform is actually the Laplace transform of some function that we can write down explicitly. For that reason, we use that as a proposed solution. Y of t equals y naught times exponential negative at plus exponential negative at convoluted with f at t. That seems to be a reasonable guess for the solution. And to be explicit, that equals y naught of exponential negative at plus the integral from 0 up to t of f of s exponential of negative a times t minus s ds. Okay, that is our proposed solution. Now let's check whether that actually is a solution. For that reason, we just need to calculate explicitly the derivative of y of t and then check that it satisfies the differential equation. So the time derivative of y, okay, that is the time derivative of y naught exponential negative at plus the time derivative of that integral, the integral from 0 to t of f of s exponential negative a t minus s ds. The first summand is easy to calculate, but the second summand, the derivative of the integral, is a bit more complicated. So we see that the time variable not only shows up in the integrand, but also in the integration bounds. The formula to use here is the Leibniz integral rule. The time derivative of the integral from 0 to t of f of s exponential negative a t minus s ds equals f of t exponential negative a t minus t plus the integral from 0 to t of the time derivative of f of s exponential negative a t minus s ds. Okay, we can write this as a sum. The first term here, f of t exponential negative a t minus t, of course simplifies to f of t. So let's take a look at the integral of the time derivative. And there we just see, okay, the integral from 0 to t of the t derivative of f of s exponential negative a t minus s ds just equals negative a of the integral from 0 to t of f of s exponential negative a t minus s ds. That's just taking the derivative of an exponential function. So in summary, plugging that all together, the time derivative of y equals negative a y naught exponential minus at plus f of t minus a times the time derivative from 0 to t of f of s exponential negative a t minus s ds. Now, having computed the time derivative explicitly, we can regroup terms, and we recognize that just equals f of t minus a times y of t. Take the first derivative of y, and then we try to regroup that result so that we get the rest of the differential equation. And the only slightly complicated thing here is the application of Leibniz integral rule. Okay, so far we've discussed the first order differential equation, a very prototypical example. And next we will discuss the second order differential equation, the next more complicated topic, so to speak. What we will see is that whereas first order differential equations can be thought of as descriptions of exponential growth or decay processes, second order differential equations typically describe oscillatory processes where we've got some oscillations that are periodic in time. The second order differential equation that we study here has got the following form. Y prime prime of t equals negative omega square y of t minus 2 alpha y prime of t. So we've got the unknown function y, and this time the differential equation involves the function itself, the first derivative, and the second derivative. And we've got some non-negative parameters omega and alpha. Since it's a second order differential equation, we need two initial conditions, one for the function itself, y of 0 equal y naught, and one for its derivative, y prime of 0 equal v naught. The basic questions here again are whether the solution exists and whether the solution is unique. Before we proceed, let me remark that this differential equation seems to have quite a peculiar form. So we have got omega square there, we've got 2 alpha here. Why do we use such a complicated form? The reason is that if we write down the differential equation with that convention, then subsequent calculations, which are quite technical, will vastly simplify. In order to get some intuition for that, let's take a look at an example. Suppose we've got an oscillating spring. Let's say at the ceiling, you've got a metallic spring that can be stretched in the vertical direction, and you attach a weight of mass m, and now you pull the weight, or maybe you squeeze the weight upwards. What you will observe is some oscillation. The spring will move up and down in an oscillatory manner. Let's describe this in terms of a differential equation. So at time t, we write y of t for the vertical position of the spring, and we denote its velocity by v of t. Now obviously the velocity is the first derivative of the position. So we got y prime of t equals v of t. Now the change of the speed, that is the acceleration, obeys the following law. M v prime of t equals negative y of t minus beta v of t. Now m times v prime, that is mass times acceleration, of course is a fourth term, and this differential equation essentially describes what is known as Hooke's law, which you might know from your physics classes. In this context, k is a positive term known as a Hooke constant of that spring, and let's ignore the last term, beta vt, for the time being. What that equation essentially tells us is that the mass experiences a force in the opposite direction of the displacement. So if you've got, let's say, a stable initial position, where y has position 0, if you squeeze it upwards, there will be a force downwards trying to push the spring into its balance position. Similarly, if you pull down the spring, that is y becomes negative, then there will be an upwards acceleration. That is a basic form of Hooke's law, which describes the oscillation of the spring. And now to this other term, beta v of t. In this context, beta is a non-negative damping term, and generally speaking, it describes that the velocity experiences a dampening proportional to the velocity. In an ideal context, beta might just be 0, but in most practical contexts, beta has a non-negative value. Beta has a non-negative value. For example, it describes the loss of energy due to air friction. Okay, let's take a look at the system. You got y prime of t equal v of t, and m v prime of t equal negative y of t minus beta v of t. We can rewrite the system as a second order differential equation. M y prime prime of t equals negative k y of t minus beta y prime of t. We divide both sides by the mass. That yields v prime prime of t equals negative k over m y of t minus beta over m y prime of t. Now we introduce a notation omega equal square root k over m and alpha equal beta over 2m. Thus we get the second order differential equation that we have observed earlier. As already mentioned before, we would like to show the uniqueness and the existence of a solution, and the uniqueness typically is much easier to show. So let's start with that. Suppose we've got two solutions, y1 and y2, defined for non-negative times going to the real numbers. Then both of them satisfy y1 prime prime of t plus omega square y of t, y1 of t plus 2 alpha y1 prime of t equals 0. Similarly, y2 prime prime of t plus omega square y of t plus 2 alpha y2 prime of t equals 0. Let's take a look again at their difference, z of t equal y1 of t minus y2 of t. We would like to show that z equals 0 for all times. So we get z prime prime of t plus omega square z of t plus 2 alpha z prime of t equals 0, and the initial condition z0 equals 0 and z prime 0 equals 0. Now let's take a look at the differential equation and multiply it by z prime of t. We get 0 equals z prime of t times z prime prime of t plus omega square z prime of t times z of t plus 2 alpha z prime of t times z prime of t. With a sharp look, we observe that the first two terms actually are derivative in time. What we got there is 1/2 of the derivative of z prime of t square plus omega square zt square, and then we still are left with the term 2 alpha z prime of t square. And since z prime of t square is non-negative, in particular we get that 0 is greater equal 1/2 of the time derivative of z prime t square plus omega square zt square. So conclusively, we have got a non-increasing function z prime of t square plus omega squared zt square, and that non-increasing function at t equals 0 has got the initial value z prime of 0 square plus omega square z0 square equals 0. It just follows from the initial condition of the function z. And since, of course, that sum of squares is non-negative, we conclude that z of t equals 0 for all times, and that had to be shown. Thus, we get uniqueness. The technique that we've used implicitly here is a so-called energy estimate. And in fact, that topic is worth a description on its own. The second-order differential equation satisfies the so-called energy dissipation or conservation, depending on the dampening term. The energy of the system for all times, t, is E of t equal 1/2 y prime of t square plus omega square yt square. And now it's worth having a look. How does the energy develop over time? Well, we know that y satisfies y prime of t plus omega square y of t plus 2 alpha y prime of t equals 0. And that differential equation is multiplied by the first derivative of y prime of t. We then observe, similar as in the previous discussion, 0 equals y prime of t times y prime of t plus omega square y prime of t plus 2 alpha y prime of t square. And again, the first two terms are a derivative. That equals 1/2 of the derivative of y prime of t square plus omega square yt square plus that remainder term 2 alpha y prime of t square. Now we readily observe that first 1/2 of a derivative is just the derivative of the energy, E of t, and then plus 2 alpha y prime of t square. In particular, the time derivative of the energy, E of t prime, equals -2 alpha y prime of t square. If there's no dampening, that is alpha equals 0, then the energy just stays constant for all times. But if there's dampening, that is alpha is positive, then the energy decreases, in which case we've got energy dissipation. So depending on alpha, we either have got energy conservation or dissipation. And in particular, the energy at time t is bound from above by the energy at time 0, where we can easily compute that E of 0 equals 1/2 of v naught square plus omega square y naught square. So much about the uniqueness of solutions, which, as we have seen, is somewhat related to energy conservation principles. And now let's address the existence of solutions. That is going to be much more complicated in the case of second-order differential equations than it has been for first-order differential equations. The basic approach, though, is quite similar. We apply the Laplace transform to the ordinary differential equation, y prime of t equals negative omega square y of t minus 2 alpha y prime of t. We abbreviate capital Y of z for the Laplace transform of y at z. And then, using the standard results on the Laplace transform, we get z square y of z minus z y naught minus z y at 0 minus y prime at 0. That equals negative omega square y of z minus 2 alpha, the difference z y of z minus y at 0. Again, we isolate capital Y of z. We rearrange terms so that we can isolate capital Y of z, and we also plug in the initial data. So first we get z square plus omega square plus 2 alpha z. That's multiplied with y of z, and that equals z y naught plus 2 alpha y naught plus v naught. Okay, we divide both sides by the coefficient on the left, and that eventually shows us that y of z equals y naught of z plus 2 alpha y naught plus v naught divided by z square plus omega square plus 2 alpha z. So we have applied the Laplace transform to the ordinary differential equation, and then we have expressed y of z in terms of the coefficient and the initial data. So we have found a closed formula for the Laplace transformation of the solution. And now our goal is to invert the Laplace transformation. We want to reconstruct the solution from that explicit formula for its Laplace transform. Now, before we proceed with that, with some foresight, it will be helpful to actually rewrite the numerator and the denominator. On the one hand, the numerator can be rewritten as y0 multiplied with z plus alpha y0 plus v0. And in the denominator, we can complete the square, and so the denominator can be rewritten as the square of z plus alpha plus omega square minus alpha square. Okay, with that, the solution has the following Laplace transform. Capital Y of z is y0 times z plus alpha divided by the square of z plus alpha plus omega square minus alpha square plus alpha y0 plus v0 divided by z plus alpha square plus omega square minus alpha square. Okay, let's try having a look at this term. And for that purpose, we will make a case distinction in omega square minus alpha square. Depending on whether omega square minus alpha square is 0 or positive or negative, we can apply different techniques to obtain the inverse Laplace transform, to reverse the Laplace transform. The first special case that we take a look at is the most simple special case, namely when omega square minus alpha square equals 0. In that case, if we take a look at the formula for capital Y of z, we notice in the first fraction we can reduce the numerator and the denominator by a common factor of z plus alpha, and so this simplifies to y0 times 1 over z plus alpha plus alpha y0 plus v0 times 1 over z plus alpha square. These two fractions depend on z, and we can look up their transformations. We see that the first fraction is the Laplace transform of exponential negative alpha t, and we also see that the second fraction is the Laplace transform of t times exponential negative alpha t. Okay, we substitute that and apply linearity. Capital Y of z equals y0, the Laplace transform of exponential negative alpha t, plus alpha y0 plus v0, the Laplace transform of t times exponential negative alpha t. Using linearity, we see that all that is the Laplace transform of one particular function, namely y0 exponential negative alpha t plus alpha y0 plus v0 t exponential negative alpha t. That produces the formula for y of t. And in particular, in that formula of y of t, we can now factor out the common factor exponential negative alpha t. And so we arrive at the final formula y0 plus t alpha y0 plus t v0 exponential negative alpha t. We can check manually that this is actually a solution to the second order differential equation. In that special case, when omega square minus alpha square is exactly 0, what the solution formula for y of t tells us is that we will first see some movement linearly going up or down, but then some exponential decay behavior will take over. And this entire thing will decay towards 0. That is because of this exponential term, exponential negative alpha t. Let's take a look at another special case. Suppose that omega square minus alpha square is less than 0. In that case, the Laplace transform of the solution can be written down as follows. y0 times the fraction z plus alpha over z plus alpha square minus alpha square minus omega square plus the fraction alpha y naught plus v naught over z plus alpha square minus alpha square minus omega square. Now for each of those two fractions, we can look up the original functions under the Laplace transform. The first fraction has got the form z plus alpha over z plus alpha square minus beta square, where beta is the square root of alpha square minus omega square. And that is the Laplace transform of exponential negative alpha t times cosine hyperbolicus of beta times t. Similarly, in the second fraction, we can factor out alpha y naught plus v naught and multiply and divide by beta. And then we use that beta over z plus alpha square minus beta square is the Laplace transform of exponential minus alpha t times sine hyperbolicus of beta times t. With that, we can substitute and find y of z equals y naught times the Laplace transform of exponential negative alpha t of cosine hyperbolicus of the square root of alpha square minus omega square times t plus alpha y naught plus v naught over square root alpha square minus omega square times the Laplace transform of exponential negative alpha t sine hyperbolicus of square root alpha square minus omega square t. And that suggests the following solution formula. Y of t equals y naught exponential negative alpha t times cosine hyperbolicus of alpha square minus omega square t plus alpha y naught plus v naught over square root alpha square minus omega square times exponential negative alpha t times sine hyperbolicus of square root alpha square minus omega square times t. Again, in the long run, the exponential decay of exponential negative alpha t will take over, but in the short run we see some excitation of the system. Finally, we consider the case omega square minus alpha square greater than 0. So y of z can be written as y naught times the fraction z plus alpha over z plus alpha square plus omega square minus alpha square plus the fraction alpha y naught plus v naught over z plus alpha square plus omega square minus alpha square. At that point, we can look up the following Laplace transformations. We define beta as the square root of omega square minus alpha square. And then we recall that z plus alpha over z plus alpha square plus beta square is the Laplace transform of exponential negative alpha t times cosine beta of t. And beta over z plus alpha square plus beta square is the Laplace transform of exponential negative alpha t times sine of beta of t, sine beta t. We can plug this in the formula of y of z. So y of z equals y naught times the Laplace transform of exponential negative alpha t cosine omega square minus alpha square in square root times t plus the fraction alpha y naught plus v naught over square root omega square minus alpha square times the Laplace transform of exponential negative alpha t times sine of the square root of omega square minus alpha square times t. And that suggests the solution formula. Y of t equals y naught exponential negative alpha t cosine of the square root omega square minus alpha square times t plus alpha y naught plus v naught over square root omega square minus alpha square times exponential negative alpha t times sine square root omega square minus alpha square times t. So in that case, when omega square is larger than alpha square, we have this oscillatory behavior, a superposition of cosine and sine functions. Again, there's this exponential decay term. But when alpha equals 0, then this is just constant. And so, in fact, then we get this oscillation behavior that we would expect from an idealized spring, that we just have cosine and sine functions. That is, the spring goes up and down periodically. In particular, when there's no dampening, alpha equals 0, then we actually have the third case applying. So you might say that the third case actually is the most typical description of an oscillatory spring. And as you can tell, we have derived this formula rather mechanically using the Laplace transformation. In upcoming lectures, we will discuss not ordinary differential equations, but more generally partial differential equations. So let's recall what is the difference between an ordinary differential equation, an ODE, versus a partial differential equation, a PDE. Well, in an ordinary differential equation, the unknown function depends only on one variable, for example, time. One example is y prime of t equal y prime of t plus y of t plus f of t, where y is the unknown function. More generally, the unknown function may depend on several variables, for example, position x and time t. And in that case, we have got a partial differential equation where the unknown function may this time depend on several variables, and so the partial differential equation in particular may involve partial derivatives. Let's have a look at two examples for that, the heat equation and the wave equation. In the heat equation, we have an unknown function u that depends on a position x and a time t, and it satisfies the partial differential equation d over dt of u xt equals the first time derivative of u at xt equals the second space derivative of u xt plus some source term f of xt. And in the wave equation, we have that the second time derivative of u xt equals the second space derivative of u xt plus f of xt, where f is a force term. The heat equation and the wave equation are both very fundamental examples of partial differential equations. But having discussed ordinary differential equations will be tremendously helpful in also discussing partial differential equations. More about that in upcoming lectures. We've previously discussed how to apply the Laplace transformation in the solution of ordinary differential equations, and now we round up that discussion by taking a look at the so-called inverse Laplace transform. So let's recap what we've done. We have seen examples for some ordinary differential equations, and we've seen how the Laplace transform has helped us solving those differential equations. The basic recipe has been that we apply the Laplace transform to the original ODE on both sides. That provides us some equation containing the Laplace transform of the solution. In the second step, we isolate the Laplace transform of the solution. We bring it on one side of the equation. And then, in the third and last step, we somehow try to invert the Laplace transform. And I think it's not controversial that the first two steps, generally speaking, are rather easy, but the major difficulty is within the last step. We have tried looking up the Laplace transforms of some simple functions, but generally speaking, we have the idea that reverting the Laplace transform is the major difficulty in that approach. So, can we generally actually invert the Laplace transform? That is the topic of this lecture video. So, consider the Laplace transform. Let's write Laplace transform of f at z equals capital F of z. And given capital F of z, very often we can look up the original function f of t from a table. Now the question is, if we don't have a lookup table, is there some formula to describe the inversion of the Laplace transform? We would like to have a transformation Laplace inverse applied to capital F, which for every t provides the original function f of t. So just like the Laplace transform of a time-dependent function provides capital F, we would like to have a transformation that, given capital F, produces the original time-dependent function. And in fact, that is feasible. So suppose that f, defined on the non-negative real numbers, is continuous, and let us write capital F for its Laplace transform. Now let's suppose that we have got some parameter gamma, such that the following two conditions are true, namely on the one hand, the integral from 0 to infinity of the absolute value of f of t times the exponential of negative gamma t dt is less than infinity, and on the other hand, the integral from minus infinity to plus infinity of the absolute value of capital F gamma plus is ds is again a finite integral. So if both of these integrals have a finite value, then the following formula is true. The original function f of t equals 1 over 2 pi times the integral from minus infinity to plus infinity of capital F gamma plus is times exponential gamma plus is times t ds. So in principle, we can use that formula as an alternative to tables if we want to revert the Laplace transform. At this point, we recall the following fact, namely, the integral from minus infinity to plus infinity is actually just an abbreviation for taking the limit as t goes to infinity of the integral from minus t to plus t. Now, those two integrals involving capital F, it makes sense to visualize those. Capital F is a function defined on a subdomain of the complex plane, and what we do is we pick some point gamma on the real line, and then we integrate over the imaginary axis passing through that real point gamma. So you take the complex plane, you pick gamma somewhere on the real line, and then you draw a vertical axis. That's where you integrate capital F. And of course then you multiply it with this exponential term in the inverse Laplace transform. Now that formula is also called the inverse Laplace transform, and we write Laplace inverse of capital F at time t equals 1 over 2 pi times the integral from minus infinity to plus infinity of capital F gamma plus is times the exponential of gamma plus is times t ds. Using the Laplace transform and its inverse, we can switch back and forth between the original time signal f of t and its Laplace transformation f of z. Okay, we will prove the Laplace inversion formula. So suppose that f of t is, let's say, piecewise continuous and vanishes for negative t. And let's also recall the Fourier transform and the Fourier inversion formula, on which the Laplace transform will be based. For any function g, depending on time, we have got that the Fourier transform equals 1 over square root 2 pi times the integral from minus infinity to plus infinity of g of t times exponential negative ist dt. And the Fourier inversion formula tells us that g of t equals 1 over square root 2 pi times the integral from minus to plus infinity of the Laplace transform of g in s times the exponential ist ds. We already know the Fourier transform and the Fourier inversion formula, and now we apply that to the following special case. Namely, let's suppose that g of t equals f of t times exponential gamma t. Okay, the Fourier transform of g in s equals 1 over square root 2 pi, plugging in definitions and using that f of t vanishes for negative numbers, times the integral from 0 to infinity of f of t
times exponential negative gamma t times exponential negative ist dt. The integrand can be simplified. We integrate f of t times the exponential of negative gamma plus is times t. Taking a sharp look, that entire expression equals 1 over square root 2 pi times the Laplace transform of f at gamma plus is. On the other hand, we can apply the Fourier inversion formula. So recall that f of t times exponential negative gamma t equals g of t, just by definition, which equals 1 over square root 2 pi of the integral from minus to plus infinity of the Fourier transform of g in s times exponential ist ds. And now we can just plug in the Fourier transform of g. We get 1 over 2 pi times the integral from minus to plus infinity of Laplace transform of f at gamma plus is times exponential ist ds. We can divide both sides of the equation by the exponential of negative gamma t, or if you want, we can multiply both sides of the equation by the exponential of gamma t, and thus we get f of t equals 1 over 2 pi times the integral from minus infinity to plus infinity of the Laplace transform of f at gamma plus is times the exponential of gamma plus is times t ds. And that proves the Fourier inversion formula. Okay, we finished the discussion with some conceptual insights. So suppose we have got some ODE with an unknown solution y of t. Okay, Laplace transforming the ODE. Sometimes we can isolate y of z, and then getting a pre-image of y of z under the Laplace transform provides us with some solution y of t. We don't really know yet whether it's a solution or whether the solution is unique, but since we can always reconstruct the original function completely from its Laplace transform, that means that applying the inverse Laplace transform to y of z always gets us a solution y of t. And since the Laplace transform can be inverted, that in fact must be the only solution.